trouble, the transformations piece, the left, right, up, down shifts. Is that true that with a little bit of practice, that one's not so bad? Is that fairly accurate? Okay, I'm getting at least some nods. Okay, so what I want to do is just double check a couple of things on 2.5, which is the preview is the composite and inverse functions. So I just want to check a couple of examples. So let's go to a few problems and just do that. And then I want to talk a little bit about 3.1 and, well, 2.6 and 3.1 and check on those. So just a few little checks here. If we want to do question 3, and question 3, they asked us to graph the inverse. So what if we were going to graph the inverse, what would you do? So I just want to check to make sure that we are all on the same page here. There's multiple ways we could do this. What's one thing you might do?
All the x values, y values.
Take all the x's, make them y values. So I could take I could take this point here, which happens to be the point 0, 1, and these are going to be f values, f points. I'll make some corresponding f inverse points. So if the point 0, 1 is on f, what point is on f inverse? 1, 0, I hear. Yep. And I could pick, they gave us this one as well, which looks like it's over 6 up 4.5. And so the corresponding point there would be 4.5 comma 6. And so I could actually then go, okay, well here I'm going to have this point, and then here's 4.5 and 6. And I can draw the graph. I can pick a whole bunch of points. Usually what I do, I'll confess, to help me out, is I'll also remember that if I want to get the graph, I can reflect the first one over the line y equals x. So I usually use that to help me out a little bit. And so I usually draw the line y equals x. Make it so it doesn't look quite so much like it has a bend in it. And then I usually use that to draw a mirror image. And I told you, I am visually challenged with these things. And so I sometimes turn it so that the line is going straight up and down. And the nice part is any point that falls on the line y equals x is going to fall on both of them. And so I'll use the line y equals x to try to help plot that as well, and a few other points. You know, I might pick, if I want to be really precise, I might pick a few other points. So, hopefully if you're given something, you can graph the inverse. Let's come over here and let's look at question 7. And in 7, we're going to be using these two functions. So let's just do a quick check. If I want to compute g at f at 2, whoops, wrong one, 7. G at f at 2. What do I do first? F of 2. So I work from the inside out. So if I go and do f at 2, that's going to be 3 times 2 minus 1, so that's 5. So I work from the inside out. And then I'm at a fairly easy situation because now once I figure out what f at 2 is, then I just need to do g at 5. And so that's going to be 1 minus 5 squared, which is negative 24. So again, with formulas, functions, you should be able to do the computation. What if we do number 9, and I'm going to actually, just because it's getting down the page a little bit, I'm just going to rewrite the question over here. So I want to do f at g at x, and then I can still see that. This is the one that's a little trickier. This is the one that for most students is one of the little harder things to do. And so if you find it a little harder to do, you're probably not alone. So remember, the way I said to do it, if it gives you trouble, is think of it as f at something, f at box, f at rectangle. And you know how to do f at rectangle, right? That's going to be 3 times the rectangle minus 1. And then, but we don't have f at rectangle. What we have is f at g at x. Right? Instead of f at rectangle, what we have is f at g at x, and the g is 1 minus x squared. And so all I've done is I've taken out the g, and I put in this rectangle, and I put that stuff in the rectangle. And then I went back to the f, and I said, well, I know f is 3 rectangle minus 1. And instead of the rectangle, I want to have the 1 minus x squared. And the only thing I have to be careful about is that 1 minus x squared goes in parentheses. And so if I go to do the math, I'm really looking at this if I get rid of the rectangle, which is 3 minus 3x squared minus 1, or 2 minus 3x squared. So a little bit of substitution going on there, right? And the composition piece. So again, there's a couple of checks of what we should be able to do. Take a second here, and I'm going to look at the 16 to 20, and it says in those, give the meaning and the units of the inverse function, and they do say, assume f is invertible. So suppose that we assume that f has an inverse. So what we're going to do, if we start off with t equals f at h, and what I'm going to do is I'm going to rewrite this using the inverse notation. So if the original is t equals f at h, what's the inverse notation going to look like? Yep, h equals f inverse of t. And so where the original says that this is the time in minutes to bake a cake at h degrees Fahrenheit, this now is going to say that this is the temperature needed to bake the cake for t minutes, or in t minutes. I won't say for, but I'll say in t minutes. I suppose we could bake a cake for as many minutes as we wanted to, but this would be the appropriate temperature to bake the cake. So if we wanted the cake to be done in 30 minutes, the inverse is saying that to bake the cake in 30 minutes, the temperature I need is blah, blah, blah. So the difference is, are we first given the temperature and then we get the corresponding time? Or in the inverse, are we given the time and we want the corresponding temperature? This is probably one of those good examples where we might say, ooh, maybe this one, maybe it's good that they told me this has an inverse, because you might argue that there could be a couple of different temperatures that are going to bake a cake in 30 minutes or 40 minutes or what have you. So if I did something similar on 19, if I start with x equals c of w, what would the inverse notation look like? W is the inverse, yep, of x. So W is C inverse of x. And where this one actually has, this actually here is the ounces of almonds. And this gives us the calories. So the original is actually saying, you tell me the number of ounces and I will output the number of calories. Well, this one's the reverse. This one is, you tell me the number of calories, and I'll tell you the number of ounces. And so if we were writing a similar statement, we would actually say that W is C inverse of X, and that's the weight, I'll use weight instead of ounces, the weight for X calories in the almonds. Right, so it's going to give me the weight this time. So W equals is giving me the weight for X calories. We'd want to come up with some sort of a sentence. I'm fairly understanding with the sentence. What I'm really going to look for if I ask you this is I'm going to be trying to get you to recognize that the output is the weight and that the input is the calories when we do the inverse, that they've reversed each other. And if you can give me some sentence that really tells me that this particular thing is going to give me the weight as the output, if I know the input of the number of calories I want to consume. Let's look at 29 for a second. For k of x is 4x minus 10, evaluate k at 3 and k inverse at 14. I claim k at 3 is pretty easy, true? Can we all agree that k at 3 is pretty easy? Maybe. How do I do k at 3? Yeah, plug that in for x. Plug the 3 in for x, right? So k at 3 is just 4 times 3 minus 10. There's an easy way to do k inverse of 14. Right? There's a hard way. The hard way is find the inverse and plug the number in. The easy way is to recognize that when I'm going to go backwards a second, I'm doing k at 3, that's 3 comma something. And when I do k inverse of 14, that's actually, here's the right order, that's actually on the original function. Notice I'm going to point the original. That's actually telling us that on the original function, 14 is not the input, but 14 is actually the output. So instead of finding an inverse function, all I have to realize is when I have when I'm looking at an inverse value, that becomes the y. And so I'm really just going to solve that equation. I'm going to, instead of put the value of 15 in for the x, I'm going to put it in for what would be the y. And then solve the equation. So just make sure that you realize that if you're given this, if you're only looking at the original, if you're not trying to find the inverse, and they're not really expecting us to at this point, that if you're given this piece and you're given the original, this, the 14, actually is the y value, and so you do 14 equals. Let's do a quick question. See how quickly we can do this. So we have this graph. And I have all these parts to it. Part A, what's f at 0? And realize that B is intended to be right here and A is right there. So f at 0 is what? B, yeah, I heard someone say B. Right, because this is the original function, this is the original function, so the 0 is 0, comma, and when I do that, it's B. What about f at question mark is 0? What's the question mark there? A, yeah, I heard the A mumbled a couple of times. Because remember, this acts as the y on the original function, and so we're actually finding that. Now I just have to get the right order here for what they did. Yeah. So, for C, they did F inverse of 0 equals. And again, I could draw the inverse, but I don't really need to draw the inverse. What I know is if I'm given the f function, right, if I have f, I'm going to use, instead of a's and b's, if I know f at box equals triangle, that tells me f inverse of triangle equals box. So if I'm going to do this problem, here's my question mark, I'm going to put where they put it, I can actually convert this to F notation. And what that tells me is if I convert it to F notation, I just flip and flop the domain and range, and that actually tells me in not inverse notation, F at question mark is equal to 0. And then this actually becomes C part B. And then the last one they ask us to do is they tell us F inverse of question mark is equal to 0. And again, since they didn't give me anything that I really know about the inverse, my best notation or my best bet is to convert back. And so that tells me then that F at 0 is question mark, and then that becomes C part A. So there's some computational things. By the way, I have in the past put these types of questions on exams. Now I'm going to, let me see if I can give, see if we got one. I might pick an even question just because I like the even question. Yeah, I'm going to pick 38 for a second just because I like this question. The daily cost of renting a car and driving up to 500 miles a day is given by this, where M is the miles driven. And they ask us to give the domain and range of the inverse. Now, I don't know about you, but I probably would want to find the domain and range of the original function first. So let me ask you a couple of questions. First question, in the original function, so in the original, not the inverse, which variable is the domain variable? M, yep. And then the range is going to be the cost. So in the real world situation, what is the domain going to be? Zero up to how much? 500. How'd you get 0 to 500? You're right, by the way.
They said they could drive up 500 miles a day.
Up to 50 miles. And we'll say that we can actually include the 500. And why 0? Why did you stop at 0?
Is you can't drive what? You can't drive negative miles.
You can't drive negative miles. Very good, thank you. Now, how do I figure out what the cost would be, what the range would be? This is actually kind of a nice function this way. If I were to graph this, what kind of a graph would this make? What would it look like? A line. A line that's increasing left to right, or a line that's decreasing left to right? Increasing, yeah. So, to get the range, the nice part is, all I need is the y value here and the y value here, and I've got those values. So to get the range, the easy one is to do the 0. So if I put 0 in, what does that give me? 32. And then I'm going to cheat. To get the upper value, it's just going to be 32 plus 0.19 times 500. How's that for cheating? So that's for F. What if I wanted to do F inverse? What do I do?
Flip the domain.
Just flip the domain and range. So yeah, so the inverse's domain is going to be 32 comma whatever 32 plus 0.19 500 times 500 is, and the range is going to be 0 to 500. All we do is flip them, and so what happens is the variables become C and M in that order. Then they ask us on part B to find a formula for the inverse function. So I'm going to take out the function notation. And we said last class, hopefully you remember from last class, that in order to find the inverse when we have meaning, and that's what this is, this has meaning. Or in other words, if you're going, what do you mean by meaning? What we sometimes here call it is a story problem. There's a story. And when it has meaning, don't go flip-flopping the letters. Don't make the C become an M and the M become a C. When it has meaning, all we do is rewrite it into the form M equals something. So in this section, that's what we're really going to be focusing on, these problems that have meaning, and all we do is solve for the other variable. Don't make it any harder than that. And so if I solve for the other variable, what's going to happen is I'm going to subtract the 32, so I'll have C minus 32, and then I'm going to divide by 0.19. So be really careful, because I catch a lot of students, they kind of have zoned out when I'm talking about this, and they start flipping, flopping letters. At this point in time, I am not going to ask you any question that's not a story problem. Your book doesn't really want us to look at things that are not story problems to any great degree at this point in time. So these are story problems, and to get the inverse, we just flop the variable, or we just flop the equation around. And notice, by the way, they write, find the inverse function F inverse of C. So if I remove the M, and I interchange, or I put the M first, and I put that F inverse of C, notice the C is the input variable, and notice in what I wrote, the C is the input variable. Let me extend the line so it doesn't confuse you. So notice if I were to put an M here, I have something that doesn't make any sense, because this is saying the input variable is C, and so what they want is the input variable to remain C. We'll revisit a lot of this later on in the course, but I wanted to spend some time because I know that when I give homework assignments or I give tests on this material, I know it causes some trouble because you're so accustomed to flip-flopping the x and the y and solving for the new y that you're going to want to do that. And I just also know that inverses and composition are one of those topics that try as hard as your high school math teachers did, they just don't click well for most of you. And so this material that's kind of in this kind of second fifth of the course, this material tends to give students a little more trouble because it has some stuff you weren't as comfortable with from before. So it has that piecewise material, and now we have the inverses piece. So we're not as comfortable with it. So after that, just real briefly, I'm trying to make sure that we're all on the same page, literally and figuratively. We talked a little bit about concavity. So in talking about concavity, we really talked about, and just to recap, because I did this in the notes, we did concave up, concave down, concave up like a frown, or concave up like a cup, I should say, concave down like a frown. Right, so there's our shapes. Concave up, we have increasing slopes. Concave down, we have decreasing slopes. So the big things you should be able to do, just to remind you from the homework problems, and if you can't, you'll want to talk to me. You know, will be if you were given a table. From the table, can we tell whether it's concave up, concave down, or neither? Yes, in some cases you can actually plot the points and try to guess. But the way from a table you want to do this is you want to compute slopes. And if the slopes increase, you're concave up. And if the slopes decrease, then you're concave down. So you would compute the slope between these 2 points, and these 2 points. So between point 1 and 2, 2 and 3, 3 and 4, and look at those slopes and see, do they get bigger or do they get smaller? And if they stay the same, you don't have any concavity. So you really want to compute the slopes from point 1 to point 2. So again, you go point 1 to point 2, and then from point 2 to point 3 to point 4, and so on. And look at those numbers. If those numbers go up, then you have a concave up situation. If those numbers from those slopes go down, then you have a decreasing situation. That's the part that usually gives students the trouble. That's usually, they just don't know what I mean by compute the slopes. You know, problems like 3 and 4 don't give any trouble. If I ask you, here's a graph, is that concave up or concave down? Right? If I look at 3, concave up or concave down? Up. Number 4, concave up or concave down? Down, right. Usually those don't give any trouble whatsoever. The real mathematical, or one more mathematical way that you can actually tell, is if you pick 2 points on a region, line, notice this line is above the graph. If your line is above the graph, your graph's concave up. If you take 2 points and you connect them, and the line is below the graph, then you're concave down. That's one more way to do that. And then they ask a bunch of questions. Notice, come back here to 9, calculate successive rates of change for the function, and decide where it's concave up or concave down. So that's that whole slope thing again. That really is all there is to that section. If that one gives you trouble, I really want you to kind of contact me outside of class and we'll chat through it. And you'll have a good sense when you go trying to work on the Wiley Plus questions. If a lot of them give you trouble, or you have to talk to somebody else about how to do them, then you know you've had some issues. So I want to move in, and you'll get the notes here as part of a package of stuff that's coming. You can get them always online anyhow. I do the paper a little bit more as a backup for you, so that your schools don't have to print out 9 bazillion copies of things, but you can always look at them online. Chapter 3 is the shortest chapter we do in the entire course. Only has 2 sections. So we'll be in chapter 4 before you know it. So chapter 3 is almost everything we want to know about quadratic functions. So just to remind you, and you've already looked at this, is quadratic functions have an appearance that looks something like what I just boxed in. All right. Quadratic functions can be written in the form y equals ax squared plus bx plus c, where a is not 0. Hopefully you remember, quadratic functions generally have 3 things that can happen. Right? They can look something like this. I'm going to draw another one below it. These two are the same. Kind of one of the same situations. They could look like this or this. Or they can look like, let's shift it around a little bit. That or that. Or the kind of third thing that can happen is they can look like one of those two, right? Those are kind of the 3 situations. They either cross the axis, the x-axis twice, or they're just tangent to the x-axis, they touch it once, or they never touch the x-axis. A couple of questions from the previous section. What is true about the concavity of a quadratic function? What would be a statement you would make about the concavity of a quadratic function?
And then the A terms positive and negative.
Has to do with the A. Yeah, when the A term's positive or negative, you're actually being a little more sophisticated than I was even asking. By the way, in the top line, is the A term positive or is the A term negative? Positive. So in all of these, A is positive, and in all of these, A is negative. I'm going to give A a name, and it's a name we'll see at the very end of the course, so let's give it right now. A is actually called the leading coefficient. And by leading coefficient, we don't mean the number that comes first. We actually mean it's the number in front of the highest power of x with our polynomial. So if we start at the highest power of x and we count down, the leading coefficient does end up being the leading number, but it's the number in front of the highest power of x. So if the leading coefficient's positive, what's true about the concavity? It's concave up, yep. And if the leading coefficient's negative, it's concave down. And so the statement that I was really looking for you to say is in a quadratic function, it is always either concave up or it's always concave down. And I'll remind you that a lot of other functions change. Now, let me show you another one that's not in this chapter. And if we went to our old cubic function, that's not always concave up or concave down, is it? It's concave down at the start, on kind of on the left side, and it's concave up on the right side. So a lot of functions change concavity, but quadratic functions don't. So again, there's our notation. You should be comfortable with finding the zeros of a quadratic function. So typically, to find the zeros right now of a quadratic function, what you would typically do is you would either, first of all, you need to make sure it's in the form 0 equals whatever we have here. And typically, you are either going to factor, right, your favorite 6-letter F word. And if it doesn't factor, or if you don't want to try to make it factor, what did you use back in your high school math classes when it didn't factor or you didn't want to factor it? The quadratic formula. Just for giggles, I'm going to come up here. What's the quadratic formula? Let's see if we remember it. And you can sing it to me if you're at one of the schools that learned a song. And they all look back at the math teacher because I know that you actually have a song up there. You don't have to sing it to me, but I figured that would kind of convey to you. I know a little bit about your math background and what happens. Last year they sang it to me. Like, oh no, not doing that here. So what's the quadratic formula anyway?
X equals negative b plus or minus the square root of b squared minus 4ac over 2a.
Wow. Whoa. Do you want to know what, not just that he remembered the formula that I thought was so incredibly cool, but he remembered the x equals part. That was what was so incredibly cool. So yeah, so there's the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's test your memory here. Let's test your memory. We have these situations. Do you remember do you remember the feature or something about this formula that produced, and I'm going to go backwards, that produced these situations? Remember what happened in this formula that produced this kind of a situation?
When the discriminant is negative.
When the discriminant is negative. What is the discriminant? What do you mean by that?
Underneath the square root.
Underneath the square root. B squared minus 4ac, remember, is called the discriminant. And when b squared minus 4ac is negative, we have no zeros, or no x-intercepts. What produced this one? Or maybe I could go to this one. What produced this one?
It's positive?
When the discriminant is positive, you're right. That's when you get the 2 zeros or the 2 x-intercepts. So in this situations, when the discriminant is less than 0, this is when the discriminant is greater than 0. What do you think the one in the middle is? When it equals 0, you got it. And that's when we have 1 0, and that actually, if you factored it, you would have 2 identical, I'm running out of room right here, 2 identical factors. Or that's what we have that's called a double root. Later on in the course, we'll refer to that in the graph as a bounce. So they talk a little bit about that through here. So I'm going to expect you can find the zeros of quadratic functions sometimes by factoring, sometimes by the quadratic formula. They did those. By the way, the book did a nice job doing a couple of those. I will warn you, let me put this back on here a second. I will warn you that when you get doing the Wiley questions where they ask you for the zeros, if the zero does not come out neat, so if it's, for example, 7/12, if the directions do not say round your answer to 3 decimal places or 4 decimal places, if it doesn't say round, they're expecting the exact fraction. And that will happen in a few cases. So if the problem doesn't say anything about round, you probably aren't going to give anything that's a decimal in your answer. So just to warn you. So they talk a little bit about concavity. Let me go back to the document camera there and talk a little bit about concavity and finding the zeros and da-da-da. They talk through a lot of what we just said. They give a couple of examples that have to do with heights and velocities, and I'm going to let you've kind of read that and that type of thing. They talk a lot about the concavity. What I want to just take a couple of minutes to talk about is finding a formula from the zeros and the vertical intercept, which remember is probably what you thought of more in your math background as the y-intercept. And so what they're going to do, and again, this is going back in your brain cells a little bit, is they're going to say, okay, you know this value, and this value, and we're going to write the equation of the parabola. We're going to write the equation. By the way, I think you all know that a quadratic function's shape is what we call a parabola. They're going to ask us to write that equation. And in order to do that, what you're going to be looking at is the fact that the easiest way is to start off with this version. So this is what we're going to use if we know the zeros or the x or horizontal intercepts. I'll use their language. If we know the zeros or the horizontal intercepts, that's what we're going to start with. Where a is that leading coefficient, if we multiplied it out, we'd have ax squared. And R1 and R2 are the roots or the zeros. So in this problem, we have the 1 and the 3. So just to remind you of x minus 1 and x minus 3, so we just write those down. Usually students are really good at that part. They're like, okay, I've got the formula, I write those down. The hard part is finding the a. Well, that's where the other point comes in, and in this case they gave us the point 0.06. And by the way, they don't have to give us the vertical intercept. They don't have to give us, they could give us any other point. It actually doesn't matter. It's just the vertical intercept makes the math a lot easier. So at this point, all I need is the a. And so notice if you look in the book, it'll say to find the a, we just substitute in the 0.06. So to find the a, we always just substitute in a third point. Doesn't have to be the vertical intercept, but we're always going to substitute in a third point. So in this case, and we put that in for x and y, right, we get 6 is equal to 3a, and they did the math out a's too. So I'm just recreating what they have in the book. So that's kind of that's pretty much the whole section that they're going to talk about at this point in time. They're going to talk about finding the zeros, whether something is quadratic, and then writing these equations, and then a few word problems that have to do with height and velocity. So that's that whole section. And at the very end, they put those formulas that we've been using. They used R and S. I tend to use R1 and R2. Then, I'm gonna look at a few examples next time and then we'll go from there. Then they go into kind of the second form of a parabola, and it's what we call the vertex form. In the vertex form, and again, you should have read this before, in the vertex form, we use this version. So if we're given the zeros, we use what we just had in 3.1. If we're not given the zeros, we'll be given the vertex. And what's really cool in this form is HK is in fact the vertex. Now notice, be careful, because it's x minus h, and it gives us the h and then the plus k. This is very much related to, and it's why we did that before, this is very much related to horizontal and vertical shifts. Very much related to horizontal and vertical shifts. So in your notes in the book, you're going to see, hey, let's find the vertex. I'll let you play with that. They're going to do a little bit of converting this to standard form. If you're going to convert that to standard form, all you really do is multiply it all out. Right? Remember, standard form from the previous section means you're going to write it in the form y equals, or f at x equals ax squared plus bx plus c. And then they use this phrase, one I haven't used before, the axis of symmetry. What do we mean by the axis of symmetry? Have you ever heard that phrase before?
It's a vertical line that cuts the parabola in half.
It's the vertical line that cuts the parabola in half. Yeah, there's a particular point, too, that vertical line passes through. What point does that vertical line pass through?
Vertex.
The vertex. Yeah. Right, if here's my parabola, there's the vertex. And if my vertex is HK, this is the line that's my axis of symmetry. See, I'm just boring you. You know all the answers to this, don't you? I could skip talking about all of this if I'm really boring, but maybe it helps a little, does it? Or am I really boring? Nobody's going to go out on a limb. She's really boring. At 8 o'clock in the morning, I'm really boring. So there's our axis of symmetry, and it's a vertical line. I love the precise language. It is, it's a vertical line, and all vertical lines have the equation x equals something, and so in the form that I'm using, the equation of that vertical line, that axis of symmetry, is x equals what? What'd you say? Oh, whoa. You said negative b over 2a. Yeah, in the formula we have, there's a quick way of saying it if we have the expanded version. In my not expanded version, in my a times x minus h squared plus k version, whoops, you can't see, what in here is going to give me the number that's the value associated with the axis of symmetry? H, you're right, H. So if we're given the standard form, we use the old negative b over 2a. If we're in vertex form, it's just the h. You don't need to multiply it out to do negative b over 2a. Really cool. we'll spend some time, and I don't have time to do this time, but I want you to try this. Make sure, so I'm gonna go through it a little bit next time. Make sure you take a look at this part on completing the square. Make sure if you haven't looked at that, because we're gonna do a little completing the square next time, and we're gonna convert into vertex form by completing the square. So we're gonna do that, so make sure that you look at that. Otherwise, just real briefly, I have about a minute and a half, we can actually find the formula given the vertex and another point. So notice here we're given 2 points rather than 3, and one of them is the vertex. And so just real quickly to make sure that you're comfortable with all of this, what we do is we start with, and I'm going to write it this way, a times x minus h squared plus k. And I'm going to run through just by looking at this problem. What we do is we take the vertex, which in this case is negative 3, 2, and that goes in for h and k. Just be careful, it's x minus h, so it's x minus the negative 3, and then just plus the regular k. And so we plug that in and simplify. So I did the 2 negatives, became the positive. And then just like we did the previous problem, we take the other points. So to find A, in this case we use, they gave us the y-intercept, but we could say we use the other points, and we substitute the values in for x and y and solve for A. See this here, how they have the 1/3? Please don't write it as 0.3 or 0.33333. You actually want to use the 1/3. Okay? Well, I am out of time. So are you ready to get away from me for a few days? Yes. Have a wonderful day, and I'll see you on Monday.